All right, hello all. I want to make a quick video about graphing and transforming logarithm graphs. Um, I don't want to spend too much time on the graphing of these, but I do want you to be able to um, finish your homework in ALEKS, so I just wanted you to have this to help you with that. Okay, so what does the graph of a logarithmic function look like anyway? Well, it's the inverse of an exponential function. So we're going to start with its inverse function, which is an exponential. So our goal is going to be to graph log base 2 of x. But in order to do that, we're first going to start by graphing its inverse, which is y equals 2 to the x. We've seen this one before. We can pick a couple of points. If x equals 0, then 2 to the x is 2 to the 0 power, which is 1. And if x equals 1, then y equals 2 to the x is 2 to the first power, which is 2. So I've got the points 0, 1, and 1, 2 on this graph of y equals 2 to the x. This is an inverse function. Our base is greater than 0, so this is going to be an increasing exponential growth function. So this is what y equals 2 to the x looks like. Just to help us here, I'm going to add one more point over here. And let me label these. So this is 1, 2. This one is 0, 1. And this point over here is -1, 1/2. We figured out how to do this in class the other day to graph an exponential. Okay, so this is what y equals 2 to the x looks like. Now, what if I want to graph its inverse, log base 2 of x? Well, to get the inverse function, I'm going to take some points, and I'm going to switch x and y because that's what inverse functions do. So the point 1, 2 here, I'm going to switch x and y, and that will become the point 2, 1. I'm going to put that one on my graph. That is 2, 1. The point 0, 1, that becomes the point 1, 0. And this point -1, 1/2, that becomes the point 1/2, -1. So these red points, these are points on my inverse function of y equals log base 2 of x. Now, what happens when I connect the dots here is that my function looks like this. Again, this is an inverse function, so it is reflected across the line y equals x. An interesting thing here is that when we do, our horizontal asymptote from the inverse function becomes a vertical asymptote on the logarithmic function. This actually has a vertical asymptote at x equals 0. Okay, so what's the domain and range of this graph? This is y equals log base 2 of x. What's the domain and range of this guy? So domain is what x values have partners. None of my negative x values have partners, and x equals 0 doesn't have a partner because I have a vertical asymptote there. But as soon as I take a little step over here into the positive numbers, I now have partners. That's going to start as soon as I get to the right of 0. So my domain here is 0, not including 0, all the way up to infinity. Those are the x values that have partners here. And the range, these are the y values that are covered. This graph continues on down forever, so I'm going to be covered from -infinity all the way up. And this continues to go up as it goes over. So eventually 3 will be covered, and then 4 will be covered, and then y equals 5 will be covered, and eventually it's going to cover everything on up to infinity. It's just going to take a very long time. So our range here is -infinity to infinity. So this is what the graph of y equals log base 2 looks like. What about y equals log base 1/2 of x? Well, to be able to figure out what the graph of log base 1/2 of x looks like, we're going to start with its inverse function, which is y equals 1/2 to the x. That is the inverse function of log base 1/2. So that's what we're going to start with to graph this guy. So we're going to get some points here. If x equals 0, then 1/2 to the 0 power is 1. So I've got 0, 1. If x equals 1, then 1/2 to the x is 1/2 to the first power, or 1/2. And then for a third point here, if I plug -1 in for x, then I have 1/2 to the -1 power. That becomes 2. Because negative exponents give us reciprocals. Hopefully, with what we've done with exponents as of late, that will make sense to you. If not, write it out, come talk to me, and we will figure out why 1/2 to the -1 is 2. And then, so now we've got some points. We'll connect these. And you can see that this is a exponential decay function. It decreases from left to right. Let me label these. This is the point 1, 1/2. This is the point 0, 1. And this is the point -1, 2. Okay, so I have that graph. Sorry, let me switch this. So I have the graph of y equals 1/2 to the x. Now that's not the graph that I want. The graph that I'm actually looking for is log base 1/2 of x. That's going to be the inverse function of this blue one. So to find an inverse function, I'm going to switch x and y. So let's do that. This point 1, 1/2, that goes to the point 1/2, 1. The point 0, 1, that goes to the point 1, 0. And the point -1, 2, that goes to the point 2, -1. Put that in here. Okay, so now I can connect my dots here. And when I do that, this is going to look like this. Trying to get that. There we go. So that's what my inverse function will look like here. So this red one, this is the graph of log base 1/2 of x. Again, I have a vertical asymptote here at x equals 0. And the domain of this guy, again, is 0 to infinity. Hope you can see, again, the x values, no x values are covered, 0 is not covered, but as soon as we take a little step to the right, we have partners. So 0 to infinity are going to be the x values that have partners. And my range, again, this continues up to infinity. This will slowly cover everything down to infinity. And we're going to cover all the y values from -infinity to infinity. So these are what the graphs of y equals log base 2 of x and y equals log base 1/2 of x look like. So these have a lot of things in common, and there are some characteristics of these guys. The domain for these is 0 to infinity. You can see that those matched on both of these. These had a vertical asymptote at x equals 0. The range for these, again, matched. We covered everything from -infinity to infinity for the range. These had an x-intercept now. So our exponentials had a common y-intercept. Logs don't have y-intercepts, but they do have x-intercepts. And all of these log base b of x graphs will have an x-intercept at the point 1, 0. If my base b is greater than 1, I'm in this log base 2 of x case, and we're going to be increasing from left to right. There's no name for this one like there was with exponentials. We're just an increasing function from left to right. And if our base is a fraction, like it was here in log base 1/2 of x, then our graph decreases. left to right. And again, we won't be using this as much, but it's kind of a fun fact that log base b of x, this does pass the horizontal line test and is 1-to-1. That means it has an inverse function. And again, that inverse function, we've seen those already. Its inverse function is an exponential function. So that's what the graphs of logarithmic functions look like. And the next thing that we're going to do is translate these. So the transformations that we're going to be working with are going to look like this. There might be a plus or a minus out front. We can have an x minus h in here with the x, and we might have a plus or minus k out here on the end. We have a lot of programming left over from our previous homework assignments about transforming graphs, and we're going to use those right now. So this plus or minus out front, if it's a plus, then it wouldn't even be written there. You really wouldn't notice it too much. But if there's a negative out front, then what you're going to do is you're going to reflect your graph up and down over the line y, or over the x-axis, the line y equals 0. So you reflect the graph up and down over the x-axis. Just like we did before, that negative out front reflects you over the x-axis. The x plus h or x minus h in here, we are adding and subtracting inside our logarithm with x. That means that we are going to be shifting this left and right. That's our horizontal shifting. If you have x plus h, this is going to go the opposite way you think it will. So if there's an x plus h in there, that's going to shift you to the left by h units. And if you have an x minus h in there with your x, that's going to shift you to the right by h units. Again, hopefully we have that programming left over from before. If you add or subtract inside with x, horizontal shifting, and it goes the opposite way you think it will. Now, an interesting fact with log graphs, because we have this vertical asymptote here at x equals 0, if our graph shifts left or right, that vertical asymptote is going to be shifted with our function. So I'm just going to make a note here and say shift your vertical asymptote left or right with your graph. So we'll make notes of that as we go. But if you have horizontal shifting left and right, that vertical asymptote is going to go with you. And then finally, this plus k, or you might have a minus k out here on the end, that's going to give you vertical shifting up and down, and that's going to move the way that you think it will. So if you have a plus k on the end, that is going to shift you vertically up by k units. And if you have a minus k out there, that's going to shift you down by k units. So this, hopefully we have all of this left over, this programming. I also want you to remember that order matters. The order in which we perform these transformation does matter. And so the first thing that you want to do is your horizontal shifting. So I want you to shift left and right first. The second thing I want you to do is those reflections, if you have to reflect across the x-axis. And the third thing that I want you to do is your vertical shifting, where you shift your graph, here we go, your graph up or down. So order matters. You're going to go left, right, then your reflections, and then your vertical shifting. Okay, so let's try this. Let's figure out how to use these. Okay, so in each of these, let's list the order in which the transformations would be performed. I also want to make a note here of what the basic graph would be. In numbers 1, 2, 3, and 4 here, notice that the logarithm that would serve as our base, or the function that would serve as our base to give us the shape of the graph, is y equals log base 2 of x. Because that base is bigger than 1, this is going to be increasing from left to right. Okay, so that's going to be our base graph. That'll be the basic shape of 1 through 4 here, and all of these transformations will be done to that base graph. So let's start and list the transformations here that would happen to that graph. I never listed that as the base function, so I'll just label that quick. Okay, so number 1 here, the transformation that we have is going to come from in here. We are subtracting a 2 inside with x, so this is going to shift us left and right. Because it's inside with x, this will go the opposite way that we think it will. So we are going to shift this to the right 2 units. And because we're shifting this right and left, our vertical asymptote is going to go with that. So I'm just going to make a note here that our new vertical asymptote is going to be over at x equals 2. It will also shift right with our graph. All right, number 2 here. What if we're subtracting 2 on the outside instead of inside with x? Since we're outside, now what's going to happen is that minus 2 is going to shift us up and down vertically. This is going to go the way we think it will. So because it's minus 2, this will shift us down 2 units. Shifting up and down does not affect our vertical asymptote, so I don't have to make a note of that. We'll just take our graph and shift it down. All right, number 3 here. This looks a little different than the way that we've been organizing these before. So to make this make a little more sense with my brain, I'm going to reorganize this a little bit. And this is going to be negative log base 2 of x plus 1. That makes it a little bit easier to see exactly what's happening here. This negative in front of the logarithm, that's going to give us a reflection across the line y equals x. And then we have this plus 1 out here because it's on the outside. That's going to shift us up 1 unit. And I need to list these in the order that they would be performed. So the first thing that I'm going to do is reflect up and down over the x-axis. And then the second thing that I'm going to do is shift this up and down. So then I'll shift it up 1. Because we don't have any left or right movement, our vertical asymptote will stay exactly where it is, and I don't need to make a note of my new vertical asymptote. And then finally, let's look at number 4 here. Again, our base function is log base 2 of x. We've got 2 transformations here. We've got a plus 5 inside with x and a plus 3 on the outside. This plus 5 inside with x, that's going to shift us right and left. Because it's plus 5, that will shift us to the left. And this plus 3 on the outside, that's going to shift us up and down. Because it's positive, that will shift us up 3 units. Okay, and then let me list these in the order that they would be performed in. The first thing that I'm going to do is the left and right shifting. So I would shift this whole thing to the left by 5 units. And when I shift to the left, my new vertical asymptote will be x equals -5. That vertical asymptote will go to the left with my graph. And then the second thing that I'm going to do is shift my graph up 3 units. I don't have any reflections, so I don't have to do that between. I'm just going to shift left 5 and then up 3. Okay, so let's use this information to graph log base 2 of x plus 5, that whole thing plus 3. So this was the last one that we did here. So first we have to figure out what the log base 2 of x graph would look like. So my base here is going to be log base 2 of x. And we just did this one up here. So log base 2 of x. That's going to look like this red one here on the left. I'm going to have the point 2, 1, and 1, 0. I'm going to start with those as the points for my logarithm. If you didn't already have those points, then you would just pick some graphs here, or pick some x values here. So if I pick x equals 2, then I would have my y value is going to be log base 2 of 2. That says 2 to what power gives me 2? And the answer is the first power. So the answer will be 1 there. So 2, 1 is a point on my graph. And if I plugged in x equals 1, then y is going to be log base 2 of 1. Log base 2 of 1 says 2 to what power gives me 1? And the answer is 0 because anything to the 0 power is 1. So that means 1, 0 is a point on my graph. And so I can connect these. This is my base graph of y equals log base 2 of x. And now we can start doing our transformations. So let me switch colors here. The first thing that I will do is shift this whole thing 5 units to the left. So I'm going to take each of my points here and shift them 5 units to the left. Left 5. Okay, so 1, 2, 3, 4, 5 to the left. 1, 2, 3, 4, 5 to the left. And when I do that, my vertical asymptote is going to go with that. So my new vertical asymptote here is x equals -5 here. And I'll fill in that graph. Because to plot these, Alex is going to want 2 points and the asymptote. So you'll want to make sure that you put that asymptote in. Okay, so we have shifted to the left 5. And then the last thing that we need to do here is shift this whole thing up 3 units. So I'll take each of my points and go up 1, 2, 3. This one goes up 1, 2, 3. And this one goes up 1, 2, 3. And that is my new graph. And so I've made both adjustments. So I will put my final graph over here on the clean one. That's my new horizontal asymptote at x equals -5. And I will put my points in. I've got -3, 4, -4, 3. And then I just kind of popped in this last one just to have another point to help me out, but we don't necessarily need that. And that is my final transformed log graph. So I hope this helps you with the logarithm transformations. Please let me know if you have any questions as you're finishing your homework.